Hello chemists, this is Ms. Placino and you are watching screencast 4.2 on ionic bonding. Today's lesson is really going to get into how to predict the formula of an ionic compound and how to represent or draw pictures of ionic compounds using Lewis structures. So let's take a look at the do now. Using periodic trends, which hopefully are still fresh in your mind since we covered them last unit, explain why metals and nonmetals bond ionically. So pause the video and why don't you take a minute to brainstorm. I'm going to draw a couple of pictures to get us started. Hopefully based on the number of electrons that are present there, we know that we're looking at an atom of lithium, 1, 2, 3, 4, 5, 6, 7, and an atom of fluorine. Lithium is 2-1, fluorine is 2-7. Now we know that both of these elements are trying to get a full outer shell. Fluorine's going to do it by getting 8. Lithium is going to do it by getting just 2 electrons in its outermost shell. It's a very small atom. So if we think about it, the easiest way for this to happen is for fluorine to just steal the electron from lithium. Question is asking us to use periodic trends and not just trying to explain it in terms of octets. As a group 1 metal, we know that lithium has a very low ionization energy, meaning it is very, very easy to steal that electron away from lithium. It requires only a little bit of energy to take it. Fluorine has a very high electronegativity. Wow. So that means that in a bond, fluorine is really, really good at attracting electrons towards itself. So when these two interact, fluorine, when they go to bond, is going to pull really tightly or really hard on that electron, and lithium isn't going to be able to hold on to it because it has such a low first ionization energy. Therefore, it's really, really easy to get that electron to transfer, leaving us with Li plus and F minus, and that changes the electron configuration to just 2, and then, 2-8 for fluorine. So again, we're just really going to focus on this today and look at how these different ionic compounds are going to form. Just to review some of the stuff we talked about in our last screencast about ionic bonds, we know this occurs when one atom takes an electron or potentially electrons away from another atom. So what would happen is we've got 2 neutral atoms, the electrons being transferred from one to the other. That leaves us with a cation with a positive charge, an anion with a negative charge, and they're going to be held together by that attractive force. This is going to occur most frequently between metals and nonmetals. We know that metallic elements with low first ionization energies and usually 1 or 2 electrons more than a full octet are very willing to give up those electrons. And nonmetals that have high electronegativities, and they're usually just 1 or 2 electrons away from completing their octet, they've got 6 or 7 valence electrons, they're going to gain the electrons and become an anion. Ionic compounds exist as crystal lattices, a term that came up in your reading. And a crystal lattice is just a 3-dimensional network of cations and anions mutually attracted to one another. Crystal lattices are extremely organized. Here's a picture representing one. You can see we go chlorine, sodium, so on and so forth. And the reason for this organized structure is it's going to minimize the repulsive forces between like-charged ions. So this is a really low energy configuration. If you took a look at this and you tried to represent how many atoms are there, maybe you could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So maybe you think this formula was like sodium 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Chlorine 13, that's its formula. Well, we don't do that with ionic compounds. We use what's called a formula unit, where you take the ratio of the atoms in that crystal lattice and you just put it in the simplest ratio. So hopefully by taking a look, you see sodium 13, chlorine 13, we can definitely reduce that down. And that's just simply going to become NaCl, a compound that hopefully you're already pretty familiar with. Next up, I want to talk about predicting ionic formula units. So basically, by looking at the atoms present that are going to get involved with the bonding, can we figure out what that formula unit is going to be? So let's take a look at this atom to start. You can follow along in your workbook. With 12 neutrons, 12 protons, and 12 electrons. And hopefully you're recognizing that this must be an atom of magnesium. Magnesium is the only element with 12 protons in its nucleus. If we look at the electron configuration, we have just these 2 valence electrons, so it's most likely going to lose electrons, which makes sense. Magnesium is a metal. How many is it going to lose? Well, it wants to get to that octet of electrons, so it needs to lose both of those valence electrons. Below that, we've got a Bohr model of this element. With 17 protons in the nucleus, that's going to be chlorine. If you look at its valence shell, it's got 7 electrons. So this is going to try to gain electrons to complete its octet. How many does it want to gain? Well, just that 1. Any more is going to put it into, or going to give it more than 8, and that's not going to be energetically favorable. So we know that magnesium needs to lose 2 electrons, but chlorine can only accept 1 electron. Therefore, hopefully you're recognizing that we need a second chlorine atom. If we try to give both of magnesium's electrons over to chlorine, it really just can't handle it, and that reaction won't occur. So let's put another chlorine atom out there. Basically, if I just take one of those electrons and I just move it over to one of the chlorine atoms, I now have Mg+1 and a Cl-. I can repeat the process again with magnesium's other valence electron, send it over to the neutral chlorine atom, turning it into a chloride ion. Now I have Mg2+, whoops, got a little ahead of myself there, Cl-, Cl-, and I've got complete octets, 2-8, 2-8-8, 2-8-8 again for the other chloride ion. So everything is, I guess for lack of a better word, it's happy, it's stable, it's completed the octet. So I would write that MgCl2 as my formula. There are different techniques that you can use to try to predict ionic formula units, so I just want to go through a couple of them now. You can do this according to the balanced charges method. We know that matter is neutral, therefore the charges have to cancel each other out. We know that we're going to end up with Mg+ and Cl-. So if I think about that, I've got a +2 from the magnesium. I need to get this balanced out. So I don't know how many chloride ions I necessarily am going to need, but I know they better cancel out and equal 0. Hopefully this is really simple algebra, and you can see that x has to be equal to 2. And again, we end up with a formula being predicted as MgCl2. This is the method that I tend to use most frequently, the crisscross method. First thing you do is write out the ions that will form. So we've already talked about this. We know we're going to have Mg2+ ions and Cl1- ions. Usually you don't write the 1 in here when you're showing the charge of an ion, whether it's +1 or -1, but for the purpose of this, this part of the lesson, I'm going to draw it in there. Basically what happens here is the charge of the cation will become the subscript of the anion and vice versa. So I have MgCl, I'm going to take the 2 from the MgCl, from the Mg2+, and I'm going to turn that into the subscript of chlorine, or chloride ion. And I'm going to repeat the process with the subscript for chloride ions. I'm going to make that, the charge for the chloride ion, I'm going to make that the subscript of the magnesium ion. Let's get rid of those charges. We reduce the subscripts to simplest terms. That 1-to-2 ratio cannot be reduced anymore and still keep them as whole numbers, but we don't write 1 in the actual formula. It's implied. So MgCl2, you just kind of push it together, and there you have your formula of the compound. Let's do a little bit of practice with that. So let's just take a look at these 4 practice problems in your workbook. First thing you want to do is make sure that an ionic bond is going to form. So if I look, I've got Br, which is bromine, and K, which is potassium. Bromine is a nonmetal, potassium is a metal, so this is definitely going to form an ionic compound. If I look, potassium is going to turn into a +1 ion because it's a group 1 metal, and we'll lose 1 electron. Bromine is going to turn into a Br- ion, the bromide ion. It's a halogen, so it will gain 1 electron. When I use the crisscross method, I basically take 1 and 1 and I just switch their locations. So this is still going to give me KBr. Pause the video, see if you can figure it out for the next 3. We'll just put check marks next to them so you know which ones we're working on. So I've gone through and I've just written out the ions that I know are going to form based on where these elements are located on the periodic table and how many electrons they're going to need to lose or gain to get to a full octet. So if we take a look at B, A, and O, I've got the 2 and the 2 that I'm going to transfer over, giving me Ba2O2. And it's worth noting that by convention, the metal always goes first, so the positively charged ion in this case. This can be simplified down to just BaO, based on the fact that barium has a +2 charge and oxygen has a -2 charge in this compound. It's always going to be in a 1-to-1 ratio. We can do the same thing for aluminum and fluorine. When I use the crisscross method, I end up with AlF3. Each aluminum ion has a charge of +3. Each fluoride ion will have a charge of -1. So to make sure those charges are balanced and the compound is electrically neutral, I need to have 3 fluoride ions to offset the charge of the 1 aluminum 3+. Put a 1 in there, just make it a little bit easier to see. Oh gosh, I made such a mess. 1+, we'll circle that a little bit better. Again, make sure the metal is going first. So I see Li3P. And that makes sense. Phosphorus has a charge of -3 when it is the phosphide ion. Lithium has a charge of +1 when it is a lithium ion. So to keep the charges balanced, I need 3 lithium ions to balance out the 1 phosphide ion. Let's get back to the notes. Now that we know how to predict the formula unit for an ionic compound, I want to talk about going through and drawing the Lewis structure. So we'll go back to our example with MgCl2, magnesium chloride. And honestly, predicting the formula unit is a whole lot more complicated in my opinion than drawing the Lewis structure. They always take on very, very similar formats really. So the first thing you want to do is draw the Lewis dot diagram for each ion. We know we've got the chloride ion, which is going to look like that. We've got, oops, let's not do that just yet. We've got the magnesium ion. It loses its 2 outermost electrons. And I've got another chloride ion. All right. Up next, I place the ion in brackets. So basically, we use square brackets. And this is just going to kind of keep everything organized. It can get really messy with all those dots all over the place. And we put the charge of the ion outside of the brackets. So Cl usually has 7 valence electrons. When it becomes chloride and has 8, it has a charge of -1. Magnesium loses 2 electrons and becomes Mg2+. Of course, the same thing happens with that chloride ion. It becomes Cl-. And that's it. That is how you draw Lewis structures for ionic compounds. It's also perfectly acceptable to go ahead, at least in my class anyway, and write out the ionic Lewis structure using a subscript instead of drawing out all of those ions. But again, this is the format it's going to take. You're going to see your metallic element, in this case magnesium, always having an empty shell. It's going to look like there are no dots around the metal ever. Because you have to complete octets, the nonmetal is going to have 8 electrons around it. So it'll always have a full complete octet. And then, of course, the elemental symbols are going to change, the charges and the subscripts will change, but the drawings are going to look really, really similar. Let's head on back to our practice problems. All right, so we already went through and did the hard part. We figured out the formula unit. Now it's just a matter of drawing the Lewis structure. So again, we're going to draw the ions. The metallic ion is always going to just have an empty octet. The non-metallic ion is going to fill its octet. You go through and you want to put square brackets around each of the ions, and then you put the charge outside. Easy. Let's do it for BaO. Barium. Careful with the charges here. If you just look at the formula, you might think it's a 1-to-1. It is a 1-to-1 ratio, but the charges are not -1 and +1 respectively. They're 2+ for barium. And 2- for oxygen. And now you're finished with that Lewis structure. Pause the video, try AlF3 and Li3P on your own. All right, aluminum 3+, fluoride ion, fill its octet, minus. And I'm going to use the shortcut method and use subscripts instead of writing out 3 different fluoride ions. You're more than welcome to do the same. If we take a look at the last problem, we've got lithium plus, 3 of those. We're going to fill phosphorus's octet as it becomes the phosphide ion with a charge of 3 minus. And now we're done with that Lewis structure for that ionic compound. Hopefully you see that they look very similar. Again, we talked about this before, but just to kind of drill it home, your cation always has an empty octet of electrons around it, no dots, and let's put in a different color, your anions are always going to have a full octet of electrons. Keep the charges outside of the brackets, and feel free to use subscripts where needed. Yeah, you've got a couple other practice problems to work with. I highly recommend give it a shot, especially this predicting the formula unit stuff. This is usually very challenging for new chemists, and it's something that's going to come up repeatedly throughout our study of chemistry this year. Thank you very much for tuning in, and I hope this screencast was helpful.